Hello everyone, in this video I'm going to talk about the Upwind scheme and its effect on the compositional simulator that we developed recently. So first of all, let's consider that we have a simple one-dimensional computational domain um, like this, which is discretized into a number of grid cells. And let's say that we have some fluid in this system which we're going to simulate, and the fluid consists of a number of components. To this end, we need to write a mass conservation equation for each of the components in the system. Component I, in this case, I is the index, which could be any of the components in the system. And we assume that we have no chemical reactions. And as you see, there is no term in this equation accounting for the generation or consumption of components due to chemical reactions. So what we have here is only the component or the mass flux term, the component source or sink term, and the component accumulation term. What is important to us here in the Upwind scheme is the component flux term. Component flux term itself consists of two terms. The first one written here is the component advective term, and the second one is the component diffusive dispersive term. The Upwind scheme is only used in the component advective term. So let me tell you why is it used here and what it does actually. So in this equation, as you see, we have some properties like phase density, the mole fraction of component I in phase J, for the evaluation of Darcy's velocity, we have phase relative permeability, phase viscosity, and some other properties of phase saturation, and yeah, things like that. But the point is that for the evaluation of properties in the component advective term, we need to use the Upwind scheme. Why? Let me show you what the reason is. So let's consider that we have a fluid, we have a phase that is flowing from the left cell to the right cell like this. And so we need to evaluate the advective term for this component, for the components in that phase. In order to do that, we use the Upwind scheme, which means that we use the information of the cell from which the component is coming. All right? The upstream scheme or the Upwind scheme. We use the information of the upstream cell. We use the information of the upwind cell or the cell from which the information is coming. The wave is coming. All right. So, for example, in this case, for the evaluation of the advective term, we use the phase density of this cell. We use the mole fraction of the component that we have in phase J in this cell. All right. And even for the evaluation of Darcy's velocity of phase J, we need to use properties like phase relative permeability. Even phase relative permeability should be evaluated and should be used from this cell. and also phase viscosity. All right, these parameters should be from actually from this cell. So when we want to evaluate the flux of, or the advective, more accurately, the advective flux of the component at this interface, when we want to evaluate that, we need to use these properties at this cell. All right. If the component was moving in the opposite direction, in this direction, we had to use we had to use those properties in this cell. All right, perfect. But the point is that, as you probably noticed, I didn't talk about this density because we actually have to use the centered scheme or the average scheme actually to evaluate phase density in this part of the advective term. All right, so now let me show you actually how this Upwind scheme is implemented in the compositional simulator that we developed. All right, so here we have the residuals, which are actually the residuals of mass conservation equations. This is the accumulation term, but what I'm gonna talk about here is this flux term. In our simulator, I have only considered the component advective term, and as you see, the component flux term is only equal to actually the advection of the components. We don't have diffusion dispersion here, and as you see, we have density, phase density, and mole fraction of different components. Component I, different components in phases that we have. All right, gaseous phase, liquid phase. If we have only liquid phase, the gaseous phase will be 0, or the densities will be 0, and so the phase that doesn't exist will be ignored. So as I said, this phase density and X must be upwinded, and we have done it here in this part. So here we iterate over all the interfaces, and what happens here is that, for example, in this case, if the velocity of the gaseous phase is positive, this is how we apply the Upwind scheme. So let me show you actually how this works. In this system, if this is actually the positive direction in our simulator, this is the positive direction. So when the velocity of the gaseous phase is positive, fluid is moving from this cell to this cell. And so let's say that this is the 0th cell, and this is the 0th interface. All right, because in Python, indices start from 0. And this is the first cell, and this is the first interface. This is the second cell, and this is the second interface. All right? So what happens here is that, as an example, if fluid is moving at this interface, the phase or actually the interface index is 0. So the interface index is 0. J is 0. So what happens here is that we use x of the 0th cell. We use x of the 0th cell, and we store it in this variable. And the same thing happens to density as well. We get the density of the 0th cell, and we put it in this vector, in this variable. All right? This is actually how we apply the Upwind scheme. If the velocity of the gaseous phase is negative, which means that the fluid is moving in this direction, we should actually use the properties of the next cell, which is J plus 1, 0 plus 1, which is equal to 1. We need to use the properties of the first cell in the advective term, and this is exactly what happens here. We get the x of J plus 1. We get density of J plus 1, and we store it in these variables on the left-hand side. And we also have the same things for liquid, all right? For the liquid phase, which I'm not gonna repeat here. So this is how we apply the Upwind scheme to these two variables, phase density and x. But as I mentioned before, we also have these two variables which needs the Upwind scheme, phase relative permeability and phase viscosity, which are used for the evaluation of phase velocities. Phase velocities we have here, which are Darcy's velocities, and they are evaluated in this function, calc phase velocities. And what I can show you here is that this is actually absolute permeability of rock. This is the distance between the centroids of the cells of the domain. And here we have a very simplified form of the Darcy's law. Absolute permeability, phase relative permeability, phase viscosity, pressure difference over L. And as you see, we have ignored the effect of gravity on the Darcy's law because our domain is horizontal. All right? So we have actually ignored this term completely, and we don't have it here at all. We only have pressure difference at this point, dP here. So as I said, we need to apply KR Upwind scheme to KRG and μg, or KRL and μL, and we have them here. KRG is a function of saturation, phase relative permeability is a function of saturation. Here I have assumed that phase viscosities are independent of any variables, and so as you see, we don't have any input arguments. So if it is dependent on some variables, we have to use the Upwind scheme. But because it is not dependent on any variables, I have not applied the Upwind scheme on it at all, because we cannot do that due to the fact that it's not dependent on any variables at all. But KRG or KRL are dependent on phase saturation, and we have used the Upwind scheme here. What is done actually here is that, assuming that fluid is moving from left to right, actually, for example, for the evaluation of phase relative permeability at interface 0, at interface I, let's say 0, interface 0, I have used the saturation of the 0th cell, which is this one. All right, and the same thing here for phase relative permeability of the liquid phase, and this is actually how the Upwind scheme is applied here. But pay attention that if the fluid moves from left to right, from right to left, this is not going to work. All right, so this actually works only when fluid flows from left to right. Let's say that fluid is flowing from right to left. Even this happens. What is done here, it uses the properties of this cell, of, for example, 0th cell, and it will put the saturation of the 0th cell here, and it will use the 0th cell to evaluate the phase relative permeability at the 0th interface. So if fluid flows in the opposite direction, this part is going to fail. All right, so you should be careful with that. All right, this was, I think, the entire thing I was going to talk about. Of course, about the implementation, let me just show you the comparison of when we apply the Upwind scheme and when we don't. This is actually what happens when we apply the Upwind scheme, and I have actually validated the results against open darts, and the results are, I could say, absolutely the same, such that you cannot see different data and the deviation at all. But what you see here is when I don't apply the Upwind scheme in the Darcy's law. If I don't apply the Upwind scheme in this part on KRG or mu G is actually independent, and so the Upwind scheme doesn't matter here. But if I ignore the Upwind scheme in this part, and actually if I use the average method to evaluate the value of KRG and KRL, this deviation will be observed and will occur, and which shows that it is important to apply the Upwind scheme even to the Darcy's law. All right, so both are important. Both here, the Upwind scheme is important, and the Darcy's law, the Upwind scheme is important. But this comparison, please note that this comparison that is made here is actually only when the Upwind scheme is ignored in the Darcy's law. All right, in this point. All right, so this was, I think, all the things I was going to talk about the Upwind scheme and its implementation and some of the results, and I hope that you found it useful. And that's it, and hope you're having a great time.